Okay, so first and foremost, I would like to thank the organizers for giving me an opportunity to present this talk to you. As you can infer from the title, I will be talking about Hopf and L-infinity algebras. We've already heard a bit about Hopf algebras these days, so the introduction will be fairly short. And after that, I will tell you what these L-infinity algebras are and hopefully relate the two in an interesting manner. So the outline of the talk is as follows. We'll start out with a motivation, which will tell us, okay, why are we studying this and what are we hoping to achieve? After that, a super brief introduction, or rather a primer on Hopf algebras, followed by showing what these L-infinity algebras are. We will showcase them in two different but equivalent formulations, and then we'll relate these two. After relating these two formulations of the L-infinity algebra, we will relate L-infinity algebras themselves with Hopf algebras. After that, we'll take a short detour and take a look at the so-called Drinfel'd twist, or the twist mechanism. And before finishing off with a conclusion and summary and outlook, we'll take a look at what has actually changed in our L-infinity structure once we've actually introduced the twisting mechanism. Okay, so for the motivation, what are these L-infinity algebras? Generally speaking, they're infinite dimensional generalizations of Lie algebras, and they are not tied to one another with the Jacobi identity, but rather with a generalized higher homotopy version of these Jacobi identities. In the world of physics, they basically represent underlying geometrical structures, and they're useful in quantization issues in both gravity and field theory. There are quite a number of applications of these L-infinity algebras. One of the most famous ones would be in the Kontsevich formality theorem, which relates these L-infinity algebras, or rather the quasi-isomorphisms between two L-infinity algebras, with the existence and classification of the existence of star products and en Poisson manifolds. Another one is useful in potentially trying to understand and deepen our understanding of non-commutativity. So one such example would be in a general L-infinity algebra. We could, for example, look at the homotopy relations and make them construct and basically bootstrap star gauge invariant theories. Another such example would be introducing these non-commutative deformations via Drinfel'd twisting, part of which we'll see today, and there we use a symmetry algebra. What is our goal? It is to show that an L-infinity algebra can be equated, or rather understood, as a graded differential Hopf algebra, and also to obtain the new structure recently shown, the so-called braided L-infinity algebra from Dimitrievich, Chirich, and colleagues. Okay, so as I promised you, we will first have a short overview on Hopf algebras. What are they? They are a bi-algebra, or rather a Hopf algebra is a bi-algebra over a field K, and is equipped with an antipode map and satisfies the following relation. A sort of prototypical example, at least in the language that we're currently trying to speak, is the tensor algebra, T of V, where V is a vector space over some field K. We define the coproduct, the co-unit, and the antipode map over the basis of the vector space V, and then we extend it to higher vector spaces in such a manner. Now, the coproduct here starts from the 0th element, and if it were indeed a coproduct of 0, then we take that and define it as a unit. And here, in the second sum, we go over so-called unshuffles. A good definition of unshuffles would be the following. If you would consider a deck of cards, and if you were to do a shuffle, well, that would be just that, a shuffle. But if you were to, say, divide the deck into two parts, and then not shuffle, but make it so that the deck is organized, so it goes in ascending order and follows each suit, then what you basically did is an unshuffle. And that is exactly what we're doing here. Basically partitioned, ordered partitions. Okay. And that is it for Hopf algebras as of now. We will come back to them later. Now we will take a look at what these L-infinity structures are. So, an L-infinity algebra is a graded vector space equipped with a collection of multilinear maps that are graded totally antisymmetric of degree 2 minus I being the a number in the natural number starting from 0, and they satisfy these homotopy Jacobi identities. Now, the psi in this relation indicates the graded Kožoman sign, and it also includes in itself the sign from the parity when you permute all of these elements. Totally graded antisymmetric means the following. If you were to have a product mu of I of two elements, and if you were to switch them around, then what you do is get a sign up front that depends on the degree of those two elements. Here we make a slight also classification, or rather a further classification. If mu0 is not equal to 0, then this algebra, or rather this structure, is what we call a curved L-infinity algebra. If mu0 does equal to 0, then that is what we typically refer to as just an L-infinity algebra. How many of these homotopy relations are there? Well, infinitely many of them. And here we will showcase just the first few of them. So for n equals 0, we get mu1, mu0 equal to 0. For n equals 1, we get mu1 squared being equal to mu2, mu1, mu0, and an element, and so on. Basically, each time we get a generalized Jacobi identity that depends on the higher product itself. So for n equals 0, we have the dependence on mu1. For n equals 1, we have the dependence on mu2, and so on. It is a pattern. If mu1 squared is equal to 0, then that is what we call a derivative. An example, if mu I in general is equal to 0 for all I except for I equals 2, then we get just a regular graded Lie algebra. If, however, mu I is equal to 0 for all I that are greater than or equal to 3, then the structure that we obtain is called a curved differential graded Lie algebra. And this is a triple consisting of G, a Lie algebra, D, the derivation of degree 1, and R, a curvature of degree 2, such that these relations are satisfied. dr equals to 0, d squared x is the bracket of R and x. However, the mu I products also correspond to certain elements of these. So mu1 would be, just as indicated before, the derivation of degree 1. Mu0 would be the curvature R, and mu2 would basically be the algebra, or rather the bracket on the algebra, meaning that the homotopy relations here would be mu1, mu0 equals to 0. So this is that relation, mu1 being d, mu0 being the curvature. And here we have mu1 squared of an element, so d squared equals the bracket, mu2 of the curvature and an element. Okay, but there are actually other ways to also formulate your L-infinity algebra depending on what is it that you actually want to prove and what is it that you actually want to do. The first one was the algebra formulation, which you just saw. There's also the co-algebra formulation. In this picture, it is defined as a co-algebra with a co-derivation map D, which is of degree 1, and it satisfies the co-Leibniz rule, and it also squares the 0. Sim of L here denotes the tensor algebra sim n of L, where L is a graded vector space. Now, the pretty cool thing about this co-algebra definition, or rather formulation, is that it relates to physics, or rather the BV formalism, quite nicely, as d squaring to 0 can be correlated to the q vector of the BV formalism, which also squares to 0. The tensor products here are graded symmetric, so once again, once we switch them around, we get a sign up front, which depends on the degree of the two elements. And in general, the coproduct is given by the following. It depends, or rather is navigated by the sigma, which is a transposition map. And a non-trivial example for two elements is given right at the bottom. I'm showcasing these two equations because later on, we will see what differences happen once we use the twist mechanism. Specifically, we will consider derivations, or rather co-derivations, that are equal to sums of BIs, where these BIs are graded symmetric multilinear maps of degree 1, just as the co-derivation was. And to obtain the first few homotopy relations, just as we did before, we want to see what d squared is equal to, and then set it equal to 0. And what we get are the following equations. Once again, just writing out the first three. So B1, B0 equals to 0. Now this looks pretty familiar to the previous one where we had mu1, mu0 equals to 0. Then we have the second one, which has a dependence on B1 squared, previously mu1 squared, and B2, B0, once again, a correspondence to the mu2, mu0 from before, and the same thing happens in the last relation as well. This allows us to basically give a third definition, but rather a formal one, of a L-infinity algebra, which is as follows. A Z-graded vector space with multilinear graded symmetric maps BI, so these fellows from up there, of degree 1, such that the co-derivation D is nilpotent. Now, you may be wondering how these two are correlated. How do we go from the algebra to the co-algebra formulation, or vice versa? Well, the answer is given with the suspension map, because the main issue here is when we did it in the algebra formulation, the mu I maps had degree 2 minus I. And in the co-algebra, co-algebra formulation, all of these maps BI have degree 1. So we have to relate these two in some way one to another. We do it with this suspension map, where we basically shift the degree of one vector space by 1 to the other, and as a consequence, the maps actually get shifted in exactly the right manner as we desire. So from 2 minus I exactly to 1. Okay, now a fairly known feature is that every L-infinity algebra is actually a Hopf algebra. And also another relatively known feature is that Hopf algebras themselves admit universal calculus within their structure. This allows us to formulate the following. A curved L-infinity algebra, so one where mu0 is not equal to 0, is a graded differential Hopf algebra. Particularly, a curved L-infinity algebra is a bi-algebra with co-derivation D, once again degree 1, such that the co-Leibniz property is satisfied, so we're just taking that from before, and D once again is nilpotent, it squares to 0. It naturally inherits the Hopf algebra structure from the graded symmetric tensor algebra, and the antipode map and the co-unit satisfy compatibility relations. What's important to note here is that when we do have a Hopf algebra, the antipode is basically its defining feature and not something that brings about new limits, limitations, or restrictions to the algebra. So the same is true in this scenario as well. If we had like an L-infinity algebra that would describe a certain physical phenomena or anything, the existence of the antipode just confirms that it is indeed a Hopf algebra, but it doesn't bring about any new restrictions or anything of the sort. Furthermore, sorry, I didn't hear you, I apologize. You mean the mu0? So mu0 on the Hopf algebras, we'll get to that fairly soon. Yeah, it's not D2. Okay. So as the co-derivation was defined as the sum of BI maps, the compatibility relations above also have to be satisfied for each of these BIs. So we also have compatibility relations relating the antipode map and the BI maps. And also the same is true for the co-unit map. And now we will do the twisting mechanism and hopefully answer some of your questions. So starting from a given Hopf algebra, which I'll call H, we may twist it using the so-called twist element, F, which is invertible and satisfies two main properties. The first of these is the two co-cycle property, and the second of these is the co-unitality property. Oftentimes, just as we also saw in one of the lectures before, we employ the use of the Sweeler notation, where we can write these twist elements as linear combinations. The notation here is slightly different than what we see these days, but rest assured, this is exactly the same as we've seen. The twist element has a natural inverse, and it also can be written in a specific way in the Sweeler notation. Now, if we have an abelian twist, and abelian twists are all that I will be covering in this presentation, we get a Hopf algebra. We'll call it F-twisted H, so HF right over here, and it is characterized by one thing only, and that is the change in the coproduct. So the coproduct gets a different sort of structure. Everything else remains the same. So the wedge product is the same. The antipode, where the twist not abelian would get changed, but since it is abelian, does not get a difference. The co-unit is the same. And also on the level of vector spaces, these two, F-twisted H and the original H, are the same. But as algebras, they're different and get a different coproduct. Why stop here, though? We can keep twisting. And we do it in the following manner. For a modular algebra A of H, there exists a modular algebra A star of HF, such that the action of the F-twisted Hopf algebra on the star-twisted A module is the same as the action of the original Hopf algebra on the original module. As vector spaces, once again, they are one and the same. However, we get a new product. So previously, we did not get a new product. Here we do. And it is obtained by precomposing the original product, mu, with the inverse of the twist. This brings about more changes to this new Hopf algebra structure. So the first thing is that, okay, obviously H star is denoted here differently. We get wedge star different. We also get a change in the coproduct once again, but also the antipode changes, regardless of the twist being abelian or not. And in these relations for the coproduct and the antipode, we get this sort of R structure, and these are elements of the R matrix, which is induced by the twist from before. So it's all a sort of iterated process. These two Hopf algebras, however, the star-twisted one and the F-twisted one, are isomorphic to one another. And there exists a map from the star-twisted to the F-twisted, given by the following relation. And it, in turn, satisfies compatibility, or rather consistency relations, these three. The phi map of the star wedge is equal to the wedge of phi's. Delta star depends on delta F, or rather not depends, but is correlated with it in this way. And S star is also related to the F-twisted antipode. If the twist were once again not abelian, we would have SF here, but since we're dealing with that, there is no such structure here. Okay, so first we said, okay, let's take a look at a general module of the algebra. Then let's say that the module algebra is equal to the Hopf algebra itself. Now let's say that the Hopf algebra itself is equal to the L-infinity structure. What we can do is we can define an action, an L-infinity action, of one L-infinity algebra as on another curved L-infinity algebra. And we get what is called an L-infinity morphism. It is a collection of graded symmetric maps of degree 0 from symmetric L to symmetric L prime, such that they define a coalgebra morphism. So delta prime phi is phi phi delta. And also, we get another compatibility relation, which relates the two co-derivations. So phi d is equal to d prime phi. Now, this is the super interesting part. These, on the level of L-infinity algebras, have their co-derivations related in the following manner. But these L-infinity algebras are also Hopf algebras. And we saw previously that due to being Hopf algebras and due to being isomorphic, the two co-products must satisfy this relation. This relation and this relation are one and the same, with just d delta prime being delta f and delta being delta star, meaning that we also get another relation here on the level of L-infinity isomorphisms, which is given right here. So we can relate the co-derivation that is F-twisted with the co-derivation that is star-twisted, meaning that if we know the homotopy relations on one of the twisted L-infinity algebras, we automatically know the homotopy relations on the other one. These phi's from before, I'm sorry, I think I haven't said it, they're a collection of graded symmetric maps of degree 0, and they act on symmetric L in the following manner. This is just a sort of consistency check and further proof. Okay, so let's do it. Let's actually get these homotopy relations in the twisted regime. So we deform delta to delta star, So how do we do it? We go from wedge to wedge star. And this is the relation that we get. Previously, I've shown you a relation that is true on the base Hopf algebra, or rather the base L-infinity algebra. It was fairly similar to this one, but the wedge products were not star wedge products, and the sigma didn't have this R with it. Rather, it didn't induce any sort of R matrix. So the difference here is that we got a new type of product, and the twist is manifest in the sigma being a transposition map. Once again, an example on two elements, a non-trivial example, and previously, once again, we had it just inverting the two elements. Now we also have it inverting the two elements, but inducing the R matrix. The co-product now satisfies, once again, it on one acting to, well, give that just that D1, and it inducing the R matrix for a general element. And the deformed homotopy relations, once again, only get a difference insofar as the BIs turn into BI stars, the wedge products turn into wedge star products, and the sigma turns into sigma R. So we define D star, once again, as the sum of BIs, just as we did before, and we can reproduce the homotopy relations by trying to figure out, or not trying to figure out, but rather demanding that D star squares to 0, that it be nilpotent. And what we get by using the equivariance of the maps BI star and the following identity is that the homotopy relations themselves remain formally unchanged. So the only difference is that the BIs turn into BI stars, and that for elements that are n equals 3 and higher, we get the R matrix elements induced within these equations. Okay, so what is the general sort of summary? Well, we have shown that a curved L-infinity algebra, it is also sometimes known as a weak L-infinity algebra, corresponds to a differential graded Hopf algebra. And we have also obtained this new structure that is called the braided L-infinity algebra. Some outlooks are, well, L-infinity algebras are always useful in physics, so a sort of deeper understanding of either field theory, quantization issues in maybe even gravity is possible. Modular-Cartan equations could also come in play here, as they effectively represent equations of motions in field theories, and also quasi-isomorphisms, seeing as they relate to physically equivalent theories one to another, could bear some new fruit in the future. And also, just as was sort of the motivation at the beginning, there might be even further applications in either non-commutative or even non-associative theories. That will be all, and thank you for your attention.
Bibliographical remark. You quote at the beginning the work by Lavin and Stashev in '92. You are perfectly right, this is a good reference. But I must say that up to homotopy structure are much older.
Oh?
Because Stashev himself did that in the algebraic topological context as early as, I would say, late 60s. Infinite and L-infinite structure up to homotopy. In that case, it was topological homotopies to understand iterated loop spaces. And so we have some links with the work of Chen that our colleague this morning mentioned of iterated integrals. So it's old stuff that being in the air, just like more recently, the Grothendieck concept appeared to light after 30 years of underground navigation.
Okay.
Naive question. Can you say more about the physical interpretation of this curved L-infinity algebra, the curving inside the new zero?
So the curved L-infinity algebra, not honestly sure what to say as of now. So this is very much I don't know what to call it, a work in progress. We don't have any examples as of yet per se, but there probably will be either some differences or something that's yet to be uncovered due to homotopy transfer not working as it does usually when the structure is curved. But to comment on what that is exactly, I sadly cannot at this point.
So maybe more a comment rather than a question. L-infinity algebras occur in the Kontsevich deformation quantization. Roughly, the principle is to find two canonical differential graded Hopf algebras. No, differential graded algebras, sorry. And you look for a morphism between these two structures. You don't find it, it's not possible, but you weaken the structures. At the level of L-infinity algebras, it works. So then maybe a vague question following this comment. Do you have an example of such reasoning using curved L-infinity algebras?
I wouldn't say so. So the thing with the quasi-isomorphisms that arise in the Kontsevich formality is that the phi1 map is not isomorphic. I am not sure how that what implications that would have for this example right here. Oh, yeah, sorry. You're welcome.
Just a simple question. Sorry, this is obvious, but this twisting element on H tensor H for the Hopf algebra twisting, it such an element always exists, or is it? If it exists?
So okay, let's just strike it back. So it does, and you can construct it not construct it, but see that it is indeed the twist element by making sure it satisfies these two relations. Yes, as far as I'm aware. Yeah, don't worry about it.
And also, this correspondence you said about the infinity and Hopf algebra, differential graded Hopf algebra, is it functorial in some way, or?
Not sure, so functorials are not my forte. I mean, in a way, I think I know that they are, but it is not something that I am like comfortable assessing, but yes, they should be, because the braided L infinity that I mentioned in a few points, that was shown using category theory. So in a way, I think that at one point, this functorial correspondence was shown or told, but do not quote me on this.